Okay, so we just finished talking about how ions, cations and anions, can be acidic or basic depending on which acids or bases they come from. If they come from a weak acid, then they will be weakly basic. But if they come from a strong acid or a strong base, they'll be neutral. So remember that salts are just ionic compounds that contain a cation and an anion. And if the cation and or anion have weak acid or base properties, then they will turn that solution into an acid or a base. So we can basically classify salts as either neutral, basic, or acidic. All right, neutral salts have a cation and an anion that are from strong acids and bases, and therefore are both neutral. So some examples of neutral salts are the classic sodium chloride, because sodium comes from sodium hydroxide, a strong base, and the chloride ion comes from hydrochloric acid, which is a strong acid. Another one would be potassium bromide. The K comes from KOH, potassium hydroxide, which is a strong base. And the bromine comes from hydrobromic acid, which is a strong acid. So all of these ions, the sodium, the chloride, the potassium, and the bromide, are all neutral ions. So when you add those to water, you have a neutral solution. They are neutral salts. Basic salts are ones that have a neutral cation. So the cation is from a strong base, and the anion is from a weak acid. So it has a weakly basic anion. So examples would be anything that has, so some of the neutral cations are sodium and potassium and lithium. All right, so sodium, fluoride, hydrogen fluoride or hydrofluoric acid is a weak acid. So fluoride is a weak base. It has a Kb. And potassium salt, that would be weakly basic, would be KNO2, because HNO2 is a weak acid. So the NO2 minus ion is weakly basic. It acts as a weak base. And then acidic salts are ones that have an acidic cation, so they come from a weak base, and a neutral anion that comes from a strong acid. So some strong acids are hydrochloric acid, hydrobromic acid. So chloride and bromide would be examples of neutral anions. So let's say ammonium chloride, all right? The ammonium ion is weakly acidic because it comes from ammonia. It's the conjugate of ammonia, which is a weak base. Whereas the chloride ion comes from hydrochloric acid, a strong acid, so it's neutral. All right? And then we could say the same actually for NH4Br. All right? This one would also be slightly acidic. So it has an acidic cation, so it makes the salt. So if you add those salts to water, it will actually make that solution a little bit acidic. So one other situation, sort of a fourth scenario, is if you have a salt that's made of an acidic cation and a basic anion. How do you know what it's going to do to the solution? Okay, so basically it comes down to that same rule of the stronger one dominates. So whichever one has the larger K value will dominate. So in this case, the NH4 ion has a Ka of 5.6 times 10 to the negative 10th, and the NO2 minus anion. So if we just look at the table and we look up these ions, what their Ka and Kb is. The Kb is 2.2 times 10 to the negative 11th. So the Ka is the larger of the two, which means that when you add this salt to water, it will form an acidic solution because the the cation is more acidic than the anion is basic. So down here it says determine if the solutions formed by the following salts are acidic, basic, or neutral. So strontium, all right, is not on our Ka, Kb table, and that's because it comes from strontium hydroxide. The cation always comes from a base. The anion always comes from an acid. So the base this comes from is a strong base, strontium hydroxide, and this one comes from HCl, which is a strong acid. So both of these ions, the strontium and the chloride, are both neutral. So this is a neutral salt, just like sodium chloride and potassium bromide that we used in the previous example. B, NH4 and F are the two ions. NH4 plus comes from NH3, the base, which is a weak base. All right, and so NH4 does have a Ka value. If we look it up on the table, it has a Ka of 5.6 times 10 to the negative 10th. And fluoride comes from HF, which is a weak acid. And fluoride has a Kb, if we look at the table, of 1.4 times 10 to the negative 11th. All right, so the Ka is higher than the Kb, so that means that this will be an acidic salt. All right, this third one, part C, sodium comes from sodium hydroxide, which is a strong base. Okay, so it does not have a Ka. All right, it is totally neutral. And the CHO2, if we look up the Kb for CHO2 on the table, it is a value of, doesn't really matter because it has a value at all, it's going to be higher. But 5.6 times 10 to the negative 6. So the Kb is higher than the Ka because there is no Ka for sodium. So this is going to be a basic salt. And then this last one I'm going to skip because we don't actually have on the table a Ka value for that anion, so we can't tell. Okay, so the next question says find the pH of each of the above solutions. I suppose it should give us a molarity in order to calculate that. So let's say they are 1 molar solutions of each of these salts. All right, so for A, the pH is going to be neutral. We're going to assume that the pH of the water that you mix it in is 7. So it's going to have a neutral pH. It's a neutral salt. So it'll have a pH of 7. For B, NH4, F, all right, when it dissolves in water, we said that the acidic component, that this the NH4 is the part that's going to make this acidic. So we can write out the equilibrium for this. NH4 will react with water to form H3O plus and NH3 base. And we can do an ice table, all right, because we know the Ka for this is, we wrote it up here, 5.6 times 10 to the negative 10. So we can figure out for a 1 molar solution of this salt, which will dissociate and have a 1 molar concentration of this. We make our ice table. We don't care about the water because it's a liquid, and pure liquids are not involved in equilibria. So initially this is 0. This goes down by x, this goes up by x. 1 minus x equals x. All right, and ultimately we want to know the concentration of this to find the pH, to take the negative log of it. So I'm going to take this equilibrium constant, 5.6 4.6 times 10 to the negative 10 equals x times x, which is x squared, divided by 1 minus x. I'm going to assume, since that Ka is really small, that this x is going to be negligible with respect to 1. So I just need to take the square root of each side of the equation. This is one of those ones where I didn't do the math beforehand. So I need to grab my calculator and 5.6 EE negative 10. The square root of that is x equals 2.4 times 10 to the negative 1, 2, 3, 4, 5. All right, so we should check this, that this is valid. 2.4 times 10 to the negative 5, is that less than 5% of 1 molar? And yes, it is. Times 100 is still 0.0024%. So this is valid. Cool, we can use this x approximation. And this is our x. So the pH is going to be the negative log of 2.4 times 10 to the negative 5. Which is 4.63. And that is what, so for a 1 molar solution of this salt, the pH, we would expect it to be 4.63, which makes sense. We expect it to be acidic because it has this weak acid here. We expected it to be acidic, and 4.63 is acidic. All right, so the other one we could do is calculate for C, this sodium CHO2, we could do that similarly. And I will do that. I don't have another slide, so I'm going to erase this and I'll do it in this place, but you might need to get another piece of paper. So I don't have more page to do this on. I took up a little too much space here, but we can figure out for C. All right, the salt is NaCHO2, and we decided it's going to be basic because there is no Ka for the sodium ion. So it's this CHO2 ion. It's going to have a minus charge after you take away that sodium. All right, it's going to react with water, and it's going to accept a proton from water and form let's say CHOOH, it's just how I'm going to write that, plus OH minus. So it grabbed one of the, it acted as a base, it accepted a proton or a hydrogen from the water, and then it became CHOOH and left us with OH minus. So again, this is a liquid. When we make our ice table, our ice box, we don't care about the water. We only care about everything else. So this we're saying is still, we're just going to say it's a 1 molar solution of this salt. And it's going to go down. These will each go up. So at equilibrium, that will be 1 minus x, and that will be x. So we're going to have the same math to do, just a different KB, okay? And also, we are calculating the concentration of OH minus, so we'll calculate the POH and then the pH. Okay, so the KB for this reaction, the equilibrium constant, is 5.6 times 10 to the negative 6. I just got that from up here. We found it on the table earlier. And that is the KB for this ion, which is basic. And the equilibrium expression x times x is x squared divided by 1 minus x. We assume that this is negligible, and we take the square root of both sides of the equation, and we get x equals 5.6 EE negative 6. The square root of that is 2.4 times 10 to the negative 1, 2, 3. All right, we should do a validity check. Divide that by 1 times 100, and that's 0.24%. So this is valid. If we do that validity check on the side, it is less than 5%. So this is our concentration of hydroxide ions. So we can use it to find the pOH. So that's going to be the negative log of 2.4 times 10 to the negative 3. So the pOH is 2.63. So the pH is just 14 minus 2.63, which is 11.37. And again, that makes sense. It's a high pH. The pH of this would be 11.37 because we expect it to be basic, because the Kb of that ion, or that ion has a Kb. It is basic. Okay, that is the end of chapter 16.